Hello students, welcome to the class. So today we are going to start a new chapter, chemical bonding and molecular structure. So in today's class I will mostly talk about the basics of this chapter and try to encourage you to go through every theory that we will see throughout the chapter. Okay, so be attentive throughout the class because this is the most important class of any chapter, which is the introduction part. According to NCERT, we will be covering NCERT section 4.1. So this is the disclaimer. If I talk about the important topics that are most valuable for your exams in the chemical bonding and molecular structure, then it will mostly focus on the types of bonding, then whisper theory. So there are multiple theories regarding the chemical bonding, and the most important one from your exam point of view is whisper theory. The next most important would be hybridization and molecular orbital theory. But before that, we have a large path to cover. So we'll move to various theories to finally come to the whisper and molecular and all. But the introduction part is still important because questions are asked from that part also. Now, from the I would say from the point of view of numerical answer type, you would see questions mainly from bond order, bond length and bond energy. So the questions will be framed in this way. Just count the number of atoms which have the same bond length or same bond order. So numerical answer type question come from this part mainly. Then we have polar and non-polar molecules and their dipole moment calculation. Lastly, of course, your exception part. So there would be molecules which would be exception to your normal trend. So we will see to that. Now, if I move to the objective of today's class, then it would be covering the Kossel-Lewis approach and important aspect of this approach, which is octet rule. Then lastly, we will see the limitations of the Kossel-Lewis approach. Try to draw some of the simple molecules also. If I move on to the NCERT section specifically, which we are covering, then they are Kossel-Lewis approach to the chemical bonding. Then in that we have subpart as octet rule, covalent bond, Lewis representation of simple molecule, formal charge, and lastly limitations of octet rule. Okay, so this is our overview of the lecture. So before moving on to the theories, let me give a clear picture of what a chemical bond is. So if you are taking two atoms, two ions and similar constituents, and then you are adding them, or I would say then you are stitching them through a strong attractive force, then that attractive force in your molecule is called as the chemical bond. So this is very fascinating to see, right? So try to think of two chlorine atoms. Now what they will do, they will be stitched to each other. So what do we symbolize? How do we symbolize this stitching part? We use a single dashed line. You must have seen various times Cl dash Cl to represent the Cl2 molecule, or you have seen the CO2 written as O, then two dashed lines C, two dashed lines and O. Now those ways are not in the literal sense. What does it mean? It means that in actual picture of the molecule, you won't see a line between two chlorine atoms. So this is just to help you visualize your chemical bond, which is connecting these two chlorine molecules. I would say two chlorine atoms, not molecules, chlorine atoms. So this is chemical bond. Now what are the theories that were developed from time to time to explain this chemical bonding? There are a lot of theories. We will only cover those which are important from the exam point of view. The first is the Kossel-Lewis approach. So this is our today's focus. Okay, now this may seem simple to you because you have seen the Lewis structure in your previous classes. If not, then I will try to make it easier as much as possible through the simple techniques. Then we will move on to the Vesper theory, the most important one, valence bond theory, and lastly, your molecular orbital theory. Okay. So let us start the Kossel-Lewis approach to chemical bonding. The first very basic thing which you would need to draw a Lewis structure is the Lewis symbol. Now, what is a Lewis symbol? So this was given by the Jane Lewis scientist, and it was mainly used to visualize the atom's valence electron. Now, this is an important part from the Kossel-Lewis approach. You have not to worry about the inner core electrons. You will be interested only in the valence electron. Therefore, your Lewis symbol is used to only represent the valence electrons. Now, what are the basic concept to draw the Lewis symbol? How do we draw it? It's very simple. As I said you, the outermost electrons are only represented, and they are the ones which are participating in bonding. Whereas the inner shell electrons, they will never participate in bonding. They will be protected by the outermost electron. If you want to visualize this inner shell electrons and the outermost electrons, then you can take a quick look on this picture. So the dashed line or the dashed concentric circle which is present on the boundary is containing the electrons known as the valence electrons. See, there are 7 electrons on this outermost shell. The remaining 2 shells which are in the inner core, that are containing 2 electrons in the first and 8 electrons in the second, these 2 can be summed together and called as the inner shell electrons. Now we have already talked about this inner shell electrons in the previous class, where we were discussing about the shielding effect. Okay, so these are acting as a shield for the outermost electron. Now, this is for the chlorine atom specifically. So we know that what is valence electron and what is inner core electron. But how do we represent it? We have seen that we can use the Lewis symbol to represent it. So let us look at the algorithm, that how do we do it. So the representation involves the valence electron represented as dots. Okay, so you represent the valence electron with the help of a simple dot, and those dots are given around the chemical symbol. Now, if you take the you would say the quantifying factor of this dot, then each dot is representing 1 valence electron. And how are these dots arranged? Very simple. Now there is not a specific way to put these dots, but we generally follow a pattern on putting out in 4 corners like top, bottom, left and right of the symbol. Example, if you look at the lithium here, then this dot is present here, right? Then on beryllium, 2 dots are present. Boron, 3 dots are present. Carbon, 4 valence electron, 4 dots are present. In the first case, it is present on the top. Here, it is present on top and bottom, then top, right and left. And in carbon, top, bottom, right and left. So on the 4 corners. Similarly, you can look up for the remaining elements given here. So this was about the Lewis symbol. Now, we will try to understand that why do these elements combine with each other. So, to understand, we should know the octet rule. So in 1916, Kossel and Lewis, they developed a very important electronic theory, which is known as chemical bonding. And it was basically explaining how the atoms combine with each other. So we know that atoms do combine, and they combine to complete their outer shell configuration of 8 electrons, and this rule is called as the octet rule. Now this octet can be completed in two ways. First is sharing of electron. Second is transfer of electron. Now here is a question for you. You can think of that element which requires electron less than 8 to complete its octet. And I would not say it octet specifically. There is a different word for that element. So I am leaving it on to you to decide that what is that word. Yes, that word is duplet. So this duplet word is used for hydrogen. Okay. And three more elements. What are those elements? Those elements are hydrogen first of all, then helium as a duplet, lithium also as a duplet, beryllium as a duplet. Okay, so these elements have a duplet. Now we will look on to the sharing of electron first of all. So we have two ways to satisfy the octet. First is sharing and second is transfer. So the sharing of electron was brought into the picture when Langmuir updated the Lewis octet idea by the introduction of this covalent bond. Okay, what is covalent bond? Bond which is formed by the sharing of electrons. Consider the formation of chlorine molecule which has a covalent bond. So why it is forming a covalent bond? Question comes to your mind, because if you look at the electronic configuration of this chlorine, then it has 7 electrons in the outermost shell. But according to the octet rule, it should have 8 electrons in the outermost shell. What it will do to satisfy this octet? It will take 1 electron which is shorting in this configuration from other atoms. Suppose we are taking the case of Cl2. So in this case, it will take electron from its identical chlorine species. And in that process, it will share 1 electron. The next adjacent chlorine atom will do the same thing. Okay. See, it is given here. The chlorine has 7 electrons on the left side. The right side chlorine also has 7 electrons. But after they are forming a covalent bond, then each of these chlorine atom is sharing 1 electron. So the area which is common in both the circles have 2 electrons. Okay, so you can see here 2 electrons are here. And if you count the number of electrons in one circle of this chlorine, so you will count it to 8. It's very easy. Similarly, for this right side chlorine, you have 7 in the uncommon area and 6 in the uncommon area and 2 in the common area. That totals up to 8 electrons of chlorine. So this is an simple example of how an element completes its octet using sharing. The next idea to complete its octet is transfer of electron. So how does it transfer electron? It transfers electron to a more electronegative element. Okay, so a less electronegative element, or I would say a electropositive element, would donate its electron to electronegative element to form ions. Now this is called as transfer of electrons, and when these two differently charged ions attract each other through electrostatic attraction, then they form a electrovalence bond. So the definition of electrovalence bond goes like this: a bond which is formed by the electrostatic interaction of positive and negative ions, or your cations or anions. Let us consider the case of NaCl. So the sodium has the configuration of a neon plus 3s1 electron. To complete its octet, it can donate 1 electron. So it will go to the positively charged species and release 1 electron. Similarly, the chlorine will gain that extra electron to form the chloride ion. Now both of these are having a noble gas configuration. Here in this case, sodium is having a configuration of neon. Now I am leaving this on to you, that what is the electronic configuration of chloride ion. since these two ionic species are oppositely charged, they will attract each other to form the electrovalence bond, which is between the Na plus and Cl minus. Yes, the correct answer for the noble gas, which is in the Cl minus configuration symbol, is argon. Okay, so instead of all of this, you can write in square bracket as iron. Now, an important term related to this electrovalence bond is electrovalence. What it is? It is simply the charge on the ion. So, if I ask you that in case of NaCl, what is the electrovalence for sodium and chlorine? So, for sodium, it is +1, and for chloride ion, it is -1. So, I guess this till this part, it is clear to all of you. It is very simple to understand what is sharing and what is transfer. Okay. Now, moving on to the next part. Of course, your HCl is a covalent one, not an ionic one. Now, what is electrovalent bond? We will talk about it in detail with the help of one more example. So, a very important part here. Now, for the time being, I am telling you that this is covalent and this is ionic. But when we will proceed through this chapter, you will find that no bond is 100% covalent and no bond is 100% ionic. So, that is an extra part to know. But I have not shown it to you now because that must be confusing. Okay, but you can keep this sentence in your mind that no bond is 100% covalent, neither they are 100% ionic. There is always a percentage of covalent and ionic character in each and every bond. Now, coming back to the electrovalent bond, we can take the example of CaF2. So, calcium is of course what? It is a metal. Now, to which group it is belonging and to what family it is belonging, it is up to you to decide. And same for the fluorine. So, I am trying to connect it with the previous chapter. Okay, now, for the time being, if I say that the calcium is a metal, okay, so you can very much clarify it with the help of the periodic table. You know it that your calcium is falling in the alkaline earth metal group or the family. Therefore, it will be a good metal and it will donate its electron to form the Ca2+. Yes. And what about fluorine? The fluorine will be a non-metal and it will belong to a 17th group. Okay. So, to gain its octet, it will take one electron and form the fluoride ion. Now, how I will write its complete formula? Very simple. Just cross multiply this valency and this will give you CaF2. So, to keep this compound overall neutral, we do this. One calcium has a charge of 2 plus, fluoride has a charge of 1 minus. So, you take 2 fluoride ions and 1 calcium 2 plus ion. And that gives you your neutral CaF2, or you can write it as Ca2 plus and F minus with a coefficient of 2. Now, what is the valency? Electrovalence, not valency, I would say electrovalence of calcium here. It is +2. And what about the chlorine atom? Or in this case, the fluorine atom, I would say. What would be the electrovalence of fluorine? It will be -1. Okay, that will be -1. For fluorine, it will be -1. Okay, so it is always the charge on the atom, not the overall charge on the fluorine. Okay, so this should be remembered. Now we know that how to represent a given element and how to represent its valence electron. Then we know that why they are combining. So we will try to now combine them and represent that combination through the Lewis dot structure. So what is a Lewis dot structure? It is a diagram that only shows the valence electron as dots around the atom, and through these dots they are trying to make bonds. Okay. Now there are two parts here. When they are sharing an electron and forming a bond, there are two parts to be considered. First is the electron pairs which are involved in bonding are called bond pair, and those electron pairs which are non-bonded are called lone pair. Now questions are often asked from this part. Okay, the molecules are not so simple, they are complex. So you may be asked to write the number of lone pair on PCl5 or SF6. So that would be a question. But questions are asked. So you must understand that what is bond pair and what is lone pair very clearly. Now, why are they combining? We already know it. They are combining it to get the noble gas configuration. Let us take the example of carbon tetrachloride to understand the same. So, what is the electronic configuration of carbon? It will be 2s2 2p2 for the valence shells and helium for the inner core electrons. So, it has total of 4 valence electrons in the outermost shell. So, there are two possibilities now. Either it can donate the 4 electrons or it can accept or share the 4 electrons. So, 3 possibilities I would say. The first 2 arises from the transfer. The last one arises from the share. So, what it will do in case of CCl4, since both are non-metals, therefore, carbon will share it. Okay, so it needs 4 electrons to complete its octet and it will do through sharing. But what we have to do? We have to represent all of these through a Lewis symbol or the Lewis structure. So first of all, we draw the Lewis symbol of carbon. It's very simple. A carbon, then 4 valence electron with dots. Then what about the chlorine? It has 1 valence electron requirement. Okay, so it has requirement of 1 valence electron. Now, the 7 electrons can be shown through this diagram. You can see chlorine symbol is in the middle and 7 dots are there around the chlorine atom to represent its valence electron. So now we have the Lewis symbol of carbon and we have the Lewis symbol of chlorine. We also know that carbon needs 4 electrons and the chlorine needs 1 electron. So what it will do? It will start to share its electron. So this is the sharing. Yes. First of all, your 1 carbon requires 4. So it will take all those 4 electrons from 4 different chlorine. Okay. If it does so, 4 was the initial count for the number of electrons, valence electron, and 4 is coming for the 4 different chlorine atoms. So total electrons in the carbon are now 8 after formation of this bond. Similarly, your chlorine needs 1 electron. So it shares also 1 electron. Now this thumb rule is not applicable everywhere, that since it is needing 1 electron, so it will do the same. But in most of the cases it is seen. So 7 was already present and 1 it is taking from the sharing with the carbon. That counts up to total of 8. You can count it. It's very easy. So chlorine, then 1, 2, 3, 4, 5, 6, 7, 8. For all chlorines, it has 8 electrons. Now here is a thought process for you. If I ask you that what is the number of lone pair on the chlorine atom, then what would be your answer? How you will count the lone pair on 1 chlorine atom? So this idea that where you will do it the number of electron shares similar to the number of electrons required, it comes basically from practice. Okay, so it doesn't have a strict rule to say that. So you have to practice more and more Lewis symbols possible, and then it would be easy for you to do the same. Okay, now coming back to the question. So the number of lone pairs will be, so I am talking about the lone pairs. So this is important to notice here. So you may make mistake in this. So this is the reason I have told you in the starting that number of electron pairs. So when I'm trying to tell it pairs, then by that I mean 2. Okay, you can take 2 one at a time. Okay. So if you are taking 2 one at a time, then number of lone pair would be what? It will be number of non-bonding electrons divided by 2. Got it? So the answer would be 3 electron pairs. So what you learned, that if you want to calculate the number of lone pairs, you will simply count the number of non-bonding electrons and divide it by 2, and you will get the number of lone pairs. Remember, pair means 2, not single. Okay. So this whole thing can be shown here. Then your next question would be, then what are the number of bond pairs? Or I would say, what are the number of bond pair for one chlorine atom? It would be again one bond pair. See, the chlorine is having one bond pair of electrons. Yes. So the question can be framed in this way to make it complicated, that what is the total number of lone pairs possible in the CCl4? So for total CCl4, how many lone pairs are possible? If one is carrying 3 lone pairs, yes, it's very simple. Just multiply with the 4. So 4 multiplied by 3, that means 8 lone pairs are possible for this CCl4. 4th is a 12, not 8. 4th is a 12. 12 lone pairs are possible for this CCl4. Next question would be, what are the number of bonded pairs in the CCl4? Very simple. There are 4 bond pairs in the CCl4. Okay. I hope this is clear to you. So it is written here, 3 lone pairs on each chlorine atom. So 4 chlorine atoms are there. Therefore, total 12 lone pairs, and 1, 2, 3 and 4 are bond pairs. Got it? In this case, I have shown the CCl4 with the help of Lewis structure only. But here I have used the bond as your single dashed line instead of using the circles. Okay. So do not get confused with this single bond. They are still the Lewis dot structure. Only the differentiation is that now we are using a dashed line to represent the same. Got it? Okay. So now you are aware about how to draw the CO Lewis molecule or the Lewis symbol. So I would suggest you to try this question of CO molecule. So your time to solve this question starts now. Since it is the start of the class, I would encourage you to use the circle part. But as soon as you move through the chapter, then you should start using your lines, dashed lines. Now I have put up this question because this is an exception. It is neither forming a complete covalent bond, not a complete ionic bond. We will talk about this, okay, once the time is up. So what are the number of bonds that are possible between carbon and oxygen? I would say specifically covalent bond. How many covalent bonds are possible between carbon and oxygen? So if you are saying it 2, then isn't it seen that your carbon is not completing its octet, right? The octet of the carbon is still not complete. So if it is sharing 2 electrons, it will get 2 more electrons. So 4 were initial, 2 more were added. That will give you total of 6 electrons. So carbon is still not in the stable form. Now the question arises, why and how we will do it. So you will try it multiple times, although you will not get the proper Lewis symbol directly here. To understand this, let us move on to the solution. So step 1, so we'll go stepwise simply. Step 1 would be drawing the skeletal system. Okay, count the total number of valence electron in the carbon and oxygen atom. So for carbon it is 4, for oxygen it is 6 respectively. So there are total of 10 electrons in the valence shell of these 2 elements. Now what would the step 2? Draw the skeletal structure of CO. So this is C, this is O. Now we are not writing the dots here. So this CO will be called simply as skeletal structure. So these terminologies are of course important, because when we are reading the textbook of NCERT or any other side book, then these terminologies can confuse you. So without the dot structure, you call it as a skeletal structure. So we have done 2 steps. Now the surprising part of this question. What is that surprising part? That when you draw one single bond, then your carbon is not still completing its octet, or in the double bond also. Therefore, what you do is you take only the electrons of oxygen and make a single bond. Okay. So here what is happening? The carbon is using its 2 electrons and forming the bond. Okay. You can see here 1, 2, 3, 4. Right. Now this 2 electrons here are being used by the carbon to make that single bond, and your oxygen electrons are still intact with the oxygen. There is no change in their number of valence electron. Can you see it? So what you consider here, a very important point is being depicted here, that you are not restricted to use only the electrons of both the element at a time to form a complete bond. You can simply use the electrons of a single carbon atom or a single element to form the bond between 2 bonds. Here in this case, it is seen that carbon is only using its electron to form this bond. So these 2 electrons are coming from the carbon. You can see it. So this is the carbon. 1, 2, 3, 4. 4 electrons are around it. So do not get confused. You must be seeing that this oxygen is having 8 electrons. So this is coming from the carbon. Now these 2 electrons of carbon, so they are still of carbon, are being used to make this single bond. Okay. Again I am repeating it. The carbon has 4 electrons, 1, 2, 3 and 4. Whereas the oxygen has 6 electrons, 1, 2, 3, 4, 5, 6. Okay. Now the carbon is using its 2 electrons to make the single bond. But still it is not complete. So I will move on further. Do not take it as completed. Now you have an advantage now. What is that advantage? That your oxygen has completed its octet and your carbon is still having the electron. Okay, and it is still having an incomplete octet. When you must have drawn the Lewis symbol, there you have seen that after sharing 2 electrons, your carbon was not completing its octet, whereas your oxygen was completing its octet. But here, since we are using the both electrons of carbon only, so we don't have to be confused about the next configuration. Now this bond is called as the coordinate bond, because both of the electrons are of carbon only. And carbon is donating its 1 electron pair to form the oxygen bond. I guess it is clear to you. If not, let us move on to the complete picture to visualize this whole thing. So octet of carbon is still not complete. We can see it very clearly from the diagram. Therefore, we will make multiple bonds. So in this whole structure, what you will notice that the oxygen is sharing 2 electrons, 1, 2, okay, then 4, 5, okay. So 4 electrons are being used by the oxygen, whereas the carbon is using only 2 electrons for its sharing. Got it? Any doubt in this? Again, I am repeating it. So in the first part, what we have done, we have made that starting bond with the help of carbon's electron only, and the remaining electrons are being used by the oxygen to form the bonds. You can try this on the paper also by yourself simply and see that what is happening inside this molecule. So this is the reason I have given you, because it is complicated compared to the simpler molecules like your CCl4 or CH4. Okay. So there are 3 bonds in total now, right? And carbon is using only its 2 electrons, whereas the oxygen is using 4 electrons to make the bond. Now moving on further. So this is your final Lewis structure. Now there are much more examples of this. You can take the example of NO2 also, where there is using of only nitrogen's electron to form the bond. Now we will move to a very important concept known as the formal charge. What is formal charge? Okay, so formal charge is simply the number of valence electron of that atom in an isolated or free state, and the number of electron assigned to that atom in the Lewis structure. So it is the difference between these two. Let us try to understand this with the help of formula. So what here it is saying that you take the total number of valence electron, then you take the number of electrons when it is I would say assigned the Lewis structure. Now this is the formula to do the same, to calculate the formal charge. Very simple. Take the total number of valence electron first, then take the total number of non-bonding electrons, subtract it, and again subtract the total number of bonding electrons. Now look at this formula and try to I would say memorize it right now, because I will use this same formula in the next upcoming slide for the O3 molecule, and it is very important to understand this concept of formal charge. So this word itself has its literal meaning. Formal means something that is not permanent of the carbon, but since we are trying to visualize them as ionic species, so we are assigning a charge of unit plus or unit minus, or I would say 2 negative or 3 negative, right? So this is the simple formula. So let us try to use this formula on O3 molecule. How we'll apply it? So first, let us consider the Lewis symbol of O3. Again, the Lewis structure of O3 is quite complicated. How? See, in this case, the third oxygen is not using its single electron to form a bond. Okay, 6 of its electrons are free, non-bonded pair. The first oxygen is using its 3 electrons. Okay, and here the fourth electron. So 1, 2, 3 and 4. So the bond between the O1 and the O3 is containing electrons of the O1 oxygen. Again I am repeating it. The bond between the O1 and the O3 is containing 2 electrons, and those 2 electrons are of the oxygen 1 only, because the oxygen 3 is not using any of its electron. But in the left hand case, the O2, which is the second oxygen, is using its 2 electron and forming a double bond with the first number oxygen. Got it? So just first of all try to understand this Lewis structure. Okay, and try to solve as much as examples possible. So in your NCERT you will see a table. Okay, you will see a table of various Lewis structure. Just try to see that what is the pattern to draw the Lewis structure. Try to practice it, and that will help you ultimately to master this concept of using Lewis structure. Now we have numbered them as 1, 2 and 3, and let us try to calculate the formal charge on each of this. First of all, on the oxygen atom marked as 1, what is the total number of valence electron for oxygen? It is 6. Okay. What is the number of non-bonded electrons? It is 2. So we have written it 2 minus half the number of bonded electrons. So 6 electrons are bonded for the oxygen 1. 3 bonds are there. So 6 electrons, 6 divided by 2, 3. Now calculate this and you will get your formal charge on this oxygen marked as 1 as +1. Now try to calculate it for the O2 and O3 also. So I am giving you some time to calculate it for the O2 and O3. So what will be the formal charge on O2 and O3? Just try to use this simple formula. Number of valence electron minus, so valence electron will be same for all of these three, minus the number of lone pairs, or not the pairs, I would say, the number of non-bonded electrons minus half the number of bonded electrons. Then what would be the formal charge on O2 and O3? Okay, so I'm giving you some time, 10 seconds approximately, to think about it. Okay. So the time is up. So let us see that what is the formal charge on the remaining 2 oxygen atoms. So the number of valence electron, as I have said it will be always 6. Now, what is the number of non-bonded electrons for O2 or the second number oxygen? 1, 2, 3, 4. So minus 4. What is the number of bonded electrons to the oxygen? 2 bonds are being formed. So 4 electrons are there. So 4 divided by 2, that will give you a charge of 0. Again, I am giving you some time to calculate it for the third oxygen atom. So it's very easy. Okay. Simply use the formula of calculating the total number of valence electron minus the number of non-bonded electron minus half the number of bonded electrons to it. Remember, you can use a very shortcut method here. I will talk about that. If you know the formal charge on 2 atoms, then you can know it on the third atom. So what will be the correct answer? What is the formal charge on the third oxygen? Remember, this whole O3 should be neutral. Okay. Then and then only your formal charge will be satisfied. One is having a +1, one is having 0. So the third one will have -1. Okay. How? Again, use that simple formula. 6 is the number of valence electron, that would be same, minus the number of non-bonded electrons. So 1, 2, 3, 4, 5, 6. See, these 6 electrons are not involved in bonding. So do not count them when you are counting the number of non-bonded electrons. Minus half the number of bonded electrons. Since this third oxygen is having one single bond, therefore the number of bonded electrons are 2. Divided by 2, that will give you -1. So on one it is +1, on one it is 0, and on the third one it is -1. Now what you can consider from here? That your overall O3 molecule can be represented along with the formal charge as follows. This one will have a +1 charge, this one will have a -1 charge, and this will be neutral. Okay. So how are we deciding that which one is bonded and which one is non-bonded? See, if you see the dots, then you take them as non-bonded. Okay, you don't have to think much about it. Take the case of the oxygen containing a negative charge. How many dots are there? 1, 2, 3, 4, 5, 6. 6 dots are there. Therefore, the total number of what? The total number of non-bonded electrons will be 6. Now, how many bonds are formed by this negatively charged oxygen? Not literally negatively charged, on the basis of formal charge. Number of bonds are 1. Therefore, 2 electrons are possible. Now, 2 divided by 1 will give you 1. Just put it in the formula. 6 minus 6 minus 1. That will give you -1 as the formal charge on the third oxygen. I hope this is clear to you. How do we calculate the formal charge? It's very simple. Just try to calculate one more time in your home. Okay. So coming back to the conclusion, since this overall molecule is neutral, therefore the summation of the formal charge will always be 0 for the neutral molecules. And this overall molecule is of course neutral. Now, question arises, is there a coordinate bond present in the O3? Yes. Whenever you see the formal charge, you assume that most of the cases will have the coordinate bond. See here, this oxygen and this oxygen is forming a coordinate bond because the negatively charged oxygen is not using its electron, whereas the positively charged electron is using two of its electron to make a single bond with the negatively charged oxygen. You can see it very clearly here. Okay, because if it was not doing so, it must have how many electrons? It has 6 electrons, so it must have used only 2 electrons, but here it is using 3 bonds, so therefore it has 6 electrons going into the bonding, okay, in which the one bond is formed by the single oxygen atom only. Okay, so this bond is between the negatively and positively charged oxygen. Now this is the reason the charge is developed, because your oxygen is donating its one electron onto the oxygen and then it is making bond with the third negatively charged oxygen. Got it? Okay. Now what are the limitations to this octet rule? The first limitation is, in some molecules we see a stable structure although the octet is not complete. So you can see it for the case of LiCl. So Li is not forming a complete octet. Similarly, your beryllium is also not forming and your boron is also not forming. Boron is forming 6 valence electrons, whereas your beryllium is forming 4 valence electrons and your lithium is forming 2 valence electrons. So what we can say, that lithium, beryllium and boron all have 1, 2 and 3 valence electrons only. Therefore, they cannot form more than the given number of electrons. So their octet will be not completed. So this is true for AlCl3 and BF3 also. You can try to draw the Lewis structure for these two also. Now let us move to the next limitation. So it is not accounting for the odd number of electrons. Take the example of NO and NO2. See here, nitrogen is not again completing its octet 1, 2, 3, 4, 5, 6 and 7. And this nitrogen is having an odd number of electrons. So this is presenting an anomaly to this octet rule. Similarly, in case of nitrogen, it is having an odd number of electrons for the nitrogen case. Now here students, you have a task to do. Just try to calculate the formal charge on each of these elements of NO2. Means on both of the nitrogens and on the nitrogen and both of the oxygen. That what will be the formal charge on these 3 elements of the NO2. Okay, I am leaving this task to you. Now the next limitation would be what? It is expanded octet. So in the previous case, we have less electrons than the actual octet. Here in this case, we have extra electron than the 8 electrons. This can be seen in case of PF5, SF6 and H2SO4. See here, the phosphorus is having more than 8 electrons. So what is the total number of electrons for phosphorus? If you count the electrons, how many electrons are possible for it? It's very simple. Simply count the number of lone pairs and the bond pairs on phosphorus. So what would be the number of electrons in case of phosphorus in the bonded state of PF5? Okay, so let us count it. So 5 bond pairs are here. Okay, from each bond pair 2 electrons are coming. So that counts up to total of 10 electrons. Therefore, this one is greater than the 8 electron rule. Similarly, if you consider the case of sulfur, it will be how much? It will be 12 because 6 bond pair are possible. Right? And in case of H2SO4, if you consider the sulfur, again it is having 2 electrons. I hope this is clear to you. Now moving on to the next part. So we have seen the limitations. Now let us see some theoretical limitations. Okay. The first one is that it is not accounting for the formation of compounds by the xenon. Xenon has a complete octet, but all these noble gases like xenon, krypton, they form compounds. Okay. They are also the case of expanded octet. And the last thing is, it is not accounting about the shape of molecule. Now this was all for today's class. Now we will quickly move to the summary of what we have dealt till now. The first is that a chemical bond is formed by the attractive attraction between the atoms or ions. Now this bond is formed due to the incompleteness of the valence shell. So to complete its octet, it form bond, and it does in two ways. First is sharing, through which is formed the covalent bond. Second is transfer, where it is forming the electrovalent bond. Then how we are representing this bonded state? With the help of Lewis dot structure, where we show the valence electron as dots, and the bonding is shown through the sharing of electrons between the atoms. Then we have studied about the formal charge, which is simply the difference between the isolated state or the free state electron and the number of electrons assigned to it in the Lewis structure. Lastly, we studied about the limitations of octet rule. So the first limitation was the incomplete octet in some molecules. Second was odd electron, and third was expanded octet. So this was all for today's lecture. Thank you. Now coming back to the doubt. So I've seen one doubt in the lecture part, that you were having a difficulty in deciding the Lewis dot structure of oxygen. First of all, let us try to draw it in the simplest way possible. So this is the simplest way. Okay. Now, oxygen requires 2 electrons. What it will do? It will form bonds in this fashion. Any issues in this? But still this oxygen is left out. But the problem is that your oxygen has already completed its octet, both of these oxygen. Therefore, what it will do? It will take these 2 electrons and transfer one of its electron to the next oxygen atom. So we can show it in this way. What it is doing? It is transferring its electron to the oxygen. As a result, what we will see? That this will acquire a positive charge and this will acquire a negative charge. Okay. Here, one red one. Let me just represent it with the green molecule which is being transferred. Okay. So this green is being transferred onto here. The remaining one are here still. Now this oxygen will make a bond. Okay. Just count the number of total electrons for each of this. 1, 2, 3, 4, 5, 6, 7 and 8. Got it? So this one has a complete octet now. What about the middle oxygen? Count it. Very simple. 1, 2. Okay, so let me count it with a different pen. So 1, 2, 3, 4, 5, 6, 7 and 8. Again, its octet is complete. Now let us count it for the third oxygen. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so in this way, the octet of all is complete by the complete transfer of electrons. So this is not, I would say, a complete transfer, but a case of coordinate bond. Yeah. So it is a case of 2 electrons coming from the same atom. Got it? So this was all for today's class. Thank you. Try to draw as much as possible Lewis structure by yourself. Examples are given in the NCERT. Thank you.